I, I try to bore you for about an hour with the introduction, and then really the rest for the module. For me, I don't know how much Chachan explained this to you. For me, the idea is that I do primarily concentrate on wastewater treatment. So we'll go through the general requirements for wastewater treatment. We go through sort of quality criteria for this, and then go into treatment technologies, options, conventional treatment, and what you can do if you need higher quality at the end of the treatment works. So advanced wastewater treatment. And that's maybe something I'd like to mention straight away, that much of the stuff that you hear either between Jachan or I will sound the same, but it's not. So from a technological point of view, it's all the same. You have water that gets pumped through some containers, pipes, and equipment for the purpose of being treated and made cleaner. But the end use of the water is obviously different. So the stuff that comes out of water treatment, potable, whatever you want to call it, that would be for our consumption, for human consumption, or for use in industry or whatever. So the water quality would have to be much, much better. In wastewater treatment, obviously, it can't be completely dirty, but we have the environment still to clean up the rest of the waste for us. So the quality of the water that's supposed to be coming out of the treatment plant is of a much lower grade. And that means that some of the techniques that you'll hear for Chachan are as conventional for water treatment. On my side of the module would be advanced treatment, and I'll try to speak a bit slowly. So you hear the same stuff, but something that for Chachan is conventional water treatment on the wastewater treatment side would be quite advanced. And it's not so much that the technology is advanced, but we just call it advanced treatment for getting better water quality. And the thing to remember there also is that drinking water starts much cleaner than wastewater. So if you have a very expensive, highly efficient technology and you overwhelm that technology with very dirty water, then the technology really is wasted. It's a bit like taking a very fine comb and putting it through your hair without having washed it first. It's going to get stuck. And that's exactly the same for water treatment. So with that in mind, I shall try to share some slides. Like I said, I have a few slides to bore you with for introduction. These slides are all on GCU Learn now, so you can look at them at your leisure, and there's other material that I'll try to direct you to. A little bit for me personal, so you know who you're talking with or who's talking to you. That's my name, Ole Pahl. I'm an environmental engineer. Studied at an institution very much the same as what Glasgow Caledonian is, sort of applied science, applied sciences university. Then went to Birmingham and spent 3 very happy years of my life stirring poop, animal poop, and that was all in the context of treating the wastewater so that we remove nutrients. And that then led to my first job afterwards, working for Cranfield University and an agricultural sort of trade body, removing nutrients again from wastewaters, and all that was in the context of the European legislation on industrial pollution. So it was on IPPC regulations. That then led to work on biosolids to land and odorous emission, gaseous emissions, legal requirements, all this sort of stuff, and a very short period on energy efficiency, domestic properties. But you get the drift. I'm sort of a watery person. I like dirty water. I like compost and waste and all this sort of stuff. So that's my background. And the introduction to the class, like I said, is about water. So a little bit about water quality first. And I think of water as one of the 3 classic elements. I keep having in my head Earth, Wind, and Fire, but I think that was a pop band. But it really is. It's everywhere on the planet. Wherever you have organisms on the planet that live and are not dead or in complete hibernation, then you will find water in these places. So it's pretty much anywhere on the planet. It is pretty essential for biological functions. So life as we know it cannot happen without water. And part of that is due to it being sort of quite unique in a way as far as the chemistry is concerned. And I don't want to get too much into the chemistry. John will do much more of that with you. But there are some unique properties really that mean that water is so important. So go straight into that. Chemical structure. Like I said, I don't want to do too much of this, but molecular weight 18, you've got the heavy oxygen in the middle, and then you have two hydrogens sitting on the side. And what you get is this sort of strange, I don't know, strange, that's the sort of three-dimensional structure of the water molecule in space. So you have the oxygen at the center, and then you have the two hydrogens at the side. So it doesn't work very well in this here environment, but if I go back a little, maybe you can see me. So if you can still hear me, then I would say if I was negative, if I was the oxygen and my hands were the positive hydrogen, if you think of magnets, then normally what you would find is that the magnets would, the positively charged magnets would sort of try to get away from each other as far as possible. Because of the way the electrons are flying around and everything, you get this here strange angle between the two hydrogens, yeah, the 105 degrees. These are the hydrogens, V is the oxygen, and in space, that looks a bit like that, yeah? So, question is, what does that remember or remind you of if I stand like this? Type away if you wish. Is anybody brave enough to type what that reminds them of? No, 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 okay. It reminds me of being on the swing, trying to be clever, jumping off at a high arc, landing on my knees, crying, and having my mum standing in the playground and saying, "Come to me, my little darling." Yeah, there's the 105 degrees. And that, I think, is what I like to think of as water, because it does exactly that to pretty much anything that you can think of. So, water, we consume things, we take them into our bodies, and they either have lots of water in them or they are themselves in water. So all of our physiological sort of biochemistry is based on water. So we carry oxygen into our body through the water and we exhale carbon dioxide. We get the energy through the water, carried into our body, into our stomach, and all these sort of things. So water is, if you want, a universal transfer mechanism for all sorts of chemicals. And if you're interested, you can look into this in the structure of the water and blah, blah, blah. It all comes down to the fact that you have sort of funny things happening between the oxygen and the hydrogen, which means that within the water molecule, you have an end here where there's more electrons flying around that's negatively charged, and you have two elements here that are more positively charged. So you have in between charges. So then thinking of magnets again, the positively charged end here will try to align with the negatively charged, and that negatively charged with that positively charged element, and then you get the structure of water. And that is why water holds together quite nicely in a glass. It doesn't just disperse into the air or something. It's fairly hard. If you try to jump off a 5-meter board in the swimming pool, you will experience these bonds between the positive and negative charges because it's not easy to get in between. But also, these points are where water can carry, in particular, ions. So if you go onto the molecular level or on the cellular level, water can pass through our cell membranes, and it can carry with it, embedded in this sort of structure, all the stuff that we need. A bit of calcium to give us strong bones, and a bit of oxygen or something to make cells burn, and a bit of energy, so that we can function our metabolism. The downside of that is that the cell membranes are stupid. So they just look at something that's of this size, whatever size it may be. If that fits through a hole in the cell membrane and has a certain charge, one positive, two negative, whatever it may be, then it will fit through the cell membranes. The cell membranes don't know whether that's good stuff, say a bit of calcium, or whether it's bad stuff, say a bit of, I don't know, cyanide or something. So What I'm trying to say is that water is pretty much a universal bond, a universal carrier. So I call it here universal solvent because you can dissolve minerals and other substances. You can dissolve gases, oxygen, carbon dioxide, and all of that gets carried into our bodies, and then it gets carried to the membranes, and then into the cells, blah, blah, blah. That's the stuff. Problem is, once the stuff is in the water, it is very, very hard to separate it from the good stuff and the bad stuff. It's because water is pretty much a universal solvent for most things to do with biological life, other than long-chain fatty acids and so on. It's on the one hand very, very necessary, and on the other hand, it's very easy to pollute, and that's why we need to treat it and keep it clean. So, what also goes into that for me, and sorry about the slide, you can see German words on there. I just found it somewhere and I haven't. Okay, hands up, I haven't translated it, but I think you can see the picture and you can guess what it's all about. It's about water transport. So you have vapor transportation, and you've got stuff going through the groundwater, running off rivers, flowing in rivers, seeping through the soil, all of this stuff. The red numbers here are models, and the blue numbers are actual measurements. Doesn't matter. The interesting thing about it is that these numbers talk about the transport of water on a global scale per year in the unit of 1,000 cubic kilometers. So think of this. Think of a kilometer, make a cube out of a kilometer, multiply it by 1,000, and then multiply it by these numbers. And that is the amount of water that gets sloshed around the planet. Most of it we never see, but there is still quite a bit flowing through the rivers and down the land. That's the stuff here. So that is these sort of smaller figures. Still, the point is, for me, because water is a universal solvent, if you have a little bit of dirt here on the land, it's not the good color because it's the same color as we have in the slide, that will be taken up by the water. It will run off the hillside, it will run into the lake, it will run into the river and so on, maybe seep into the groundwater. And once it's in the water, it will disperse really finely. It won't stay as a concrete defined block, it will dissipate. So it's really easy to pollute very large quantities of water with a very small amount of contaminant. And once it's in, it's like genie out of the bottle, it disappears. And you can't get it out. So the first lesson for me is the best way to protect water quality is to not put dirt in the water in the first place. And that is something I think that's quite hard to understand for some people. It's maybe against sort of behaviors. So if you think what people do maybe in the kitchen, everybody is trained to recycle all the waste glass bottles, plastics and whatnot. So you have a carton, 2-liter bottle of milk, and the milk is out of date. So you look at it and you think, oh, it's a nice plastic bottle that should go into a plastic recycling container. So you take the old milk and you pour it down the drain. You take a bit of washing up liquid and you clean the plastic container so that you can take the plastic container and put that into the recycling. And what you've just done is you have completely outweighed the effect or benefits of recycling that glass or plastic or whatever it may be. And you replace that with lots of dirty water that you just put into the system. So the water, the milk, flows down the drain into the sewage treatment works, where somebody has to spend a lot of money and energy and therefore carbon to get it out of the water again.
Excuse me, sir.
Yeah?
Yes,
please?
sir. Sir, this is Iram. Sir, actually the language is used in the diagram is not understandable for us.
Yeah, I just explained that.
Because we are not familiar of the typical words. Kindly explain that.
I get that point, but I did say you don't need to see the words. It's about the flows. It's just an example, so don't worry about the words, yeah? The important thing is don't put waste into water in the first place, because once the waste is in the water, it will flow through the water cycle, and it will be very hard to get it out of the water again. That's the main message. So somebody explained it to me once. If you take an old carrot in the kitchen, just a carrot, so something that's not very energetically rich, and you put that into a sort of waste disposal unit that some people have in their sinks, the energy or the waste, if you want, that's contained in that mashed up carrot is the same as one person's daily waste. So think of yourselves going to the toilet and doing all the stuff. That is the same damage as putting one carrot down the waste disposal unit. So again, the message is, do not put stuff down the toilet or down the drain if it can go into a solid waste bin. Anyway, away from the German words, back to water quality. So, very brief introduction. There is, like I said, there's the issue of water quality for drinking water and for wastewater. For drinking water, we are more concerned maybe with the health hazards or with risks to human health or animal health or whatever it may be. And it's things like maybe nitrite in the water or chloride, bacteria. I'll say a little bit more about that in a short while. But it's also about cosmetic characteristics. So that could be color, taste, odor, turbidity. And that, I mean, to me, that's quite important. So, glass of water, yeah, looks fairly clean. I don't know, I've washed it. And I'd be happy to drink that, so I drink it. And hopefully I won't die of it. Why does it matter how the water looks? There's a lot of discussion sometimes around this. So if you have a problem with the water supply, there's a pipe burst or something, and the water company repairs this, then after you switch the pipe back on, the water might look quite different. It might look sort of reddish and have stuff in it. And they normally send you a message saying, it doesn't matter, it will still be safe to drink, it's fine. But it might look like this, yeah? Because you might have a bit of iron oxide in it or something. So people would say, ooh, that doesn't necessarily look good, does it? Because it has a strange color. There's now bubbles in it. There might be stuff floating in it. It has a taste, a smell, and it tastes different. So, is this safe water to drink? Our senses would tell us that this is not safe to drink because it doesn't look clear. It smells of something. It might have stuff floating in it. And in fact, it's this, yeah? A bit of Iron Brew, Scotland's national drink. So people drink this all the time. It might not be healthy, but they drink it all the time. If it came out of our tap, we would have a problem with it. So for the tap, that doesn't matter so much because we should still trust that the water that comes out of the tap is clean. But if you don't have the tap and have to decide based on your senses whether water is safe to drink, then the senses are spectacularly poorly equipped really to explain that. So 5,000 years ago or whenever we had the last ice age and we were trundling around the countryside looking for something to drink, and there's a river and we kneel down and we drink and the water has a strange taste or it smells foul and there's stuff floating in it, then there would have been a very good chance that, you know, a kilometer up the stream there would have been, I don't know, a mastodon or something died and it's decaying, and the juices of this rotting body are flowing into the water full of bacteria and stuff, and you shouldn't drink that. We don't have that so much these days. What we have is a problem much more man-made. So we put pesticides in the water and other chemicals and, I don't know, cleaning agents, pharmaceutical residues, chromium runoff from the road and all these sort of things. And these things we can't taste. We can't see them. They don't have a smell. They don't necessarily even create turbidity. So our senses are not very good. And that is why, for example, the World Health Organization has a big guide on water quality, and it explains all these sort of things like this sort of stuff, nitrate and chloride, bacteria, blah, blah, blah. But it also says that it's very important to look at these cosmetic characteristics, because in areas where you do not have safe piped water, people might decide on the safety or not of water based on what they can smell, taste, feel. And that may be the wrong way, because arguably the really dangerous stuff, E. coli or something, you cannot taste and you cannot see and you cannot feel it. So it's important to provide water that looks safe so people choose the right water. That's probably all of what I want to say about drinking water. On the wastewater, it's a different story. You still have similar quality criteria. So, for example, you have also solids in there. You may have nitrogen or forms of nitrogen. But like I said before, for wastewater, the quality criteria are much more to do with how dangerous is this water for the environment into which we pump it. So we need to not worry about whether it's bad for humans so much, because humans don't tend to drink wastewater. It becomes a problem for humans only once we discharge water into the environment, and then there's fish swimming in that environment or whatever it may be, and the fish gets polluted, and then we eat the fish and then we get damaged. So there's another step or two barrier between us and the wastewater. Or if it was bathing water areas and this sort of stuff. So the water that discharged from a wastewater treatment plant, therefore, is much, 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 much dirtier than the water that comes out of a drinking water treatment plant. And for wastewater, therefore, what you really want to know is, for the plant design or for the operation, how much of this here waste goes into your plant, and how dirty can it be when it leaves the plant. So the environmental regulator will say to you, no more than that, and you have to achieve the bit between the inlet and the outlet, and that's what the treatment plant has to do. So a little bit on some of these details maybe. Nitrate, for example. On the drinking water side, there's a European nitrate directive that says that you can't have more than 50 milligrams of nitrate, or no more than 10 milligrams of nitrogen that's contained in the nitrate in the water, because there's health issues. So it's not good for your bodies, and it's not good for babies. Let's park this for the moment. But nitrate also is important as a nutrient, because it makes plants grow, and too much plant growth, and algae growth in particular, leads to eutrophication. So for me, this is a perfect example of a quality criterion that applies both to drinking water and wastewater. But in drinking water, it is limited to a different degree than it is in wastewater. Because in drinking water, it's a human health problem, and in wastewater, it's an environmental health problem. So you need to keep this in mind when you hear the same words between Chachan and Ari, or maybe Bob Gilmore later on. It always depends on the context, so please keep that in mind. So for drinking water, the quality criterions are, like I said, nitrate, and is fluoride in drinking water, you need to have healthy teeth or not, lead, bacteria, pesticides, solids, all this sort of stuff, and then all the subjective quality cosmetic characteristics. For drinking water, that's the one thing. For wastewater, it's another thing. For wastewater, maybe you concern yourself also with things like this, total solids, which is all sorts of stuff that's in the water. So for drinking water, again, you want very little of this, because any waste and solids, particles that are in the water could form a breeding ground for bacteria, and that's not what you want in drinking water. In wastewater, it's a completely different thing, because the wastewater is naturally rich of all this stuff. So it would be almost impossible to clean that to the same level as you would expect in drinking water. I hope that makes sense. I keep saying the same stuff, but sometimes, remember we had this in an exam situation. We don't have exams anymore, but even when there's a question and it says something like, hey, why is it important to remove solids from wastewater? And if the answer to that is because it gives you a funny feeling when you drink it, that's just not right, is it? But people do that. People still sometimes forget that there's drinking water side and wastewater side, which is the right hard one about it. So excuse me for that. Anyway, sticking now firmly on the side of sort of treatment plants, the very early developments for water treatment plants go back to, as you can see there, quite some time, over 200 years ago. And there's two main types of plants. So the very early ones were these things, slow sand filters. And you can imagine that, or you should imagine that, a bit like a swimming pool, where you have the membrane at the bottom of the swimming pool with some substructure. And on top of the membrane, you just put sand. Not very much sand, maybe half a meter or so of sand. And then you put your water into that swimming pool, and the water filters through the sand. But the dirty stuff, the heavy stuff that I mentioned earlier on, these sort of solids, they start sticking to the sand a little bit and form a breeding ground for bacteria. So these sand filters would be nothing else than a very coarse filter for solids. And onto these dirty solids, you would then have bacteria growing, and that is the actual treatment. So after a while, the whole filter will be covered with a layer of sand that's infused with organic matter that is colonized by bacteria. As the water filters through these bacteria layers, the bacteria eat up the organic matter in the water, and what comes out at the bottom is basically biologically treated water. And you can see here that these filters actually started really quite early, the earliest on this slide anyway, from 1804. John Gibb Company in Paisley. So, question is, why were they developed? Why would Paisley need clean water? Any ideas? Does anybody dare type something? Farming, yeah, interesting. No. The answer is no. It's more the other way around, and maybe farming was the problem for the waste in the water. But Paisley needed it for something else. Now, Paisley is not my home ground, obviously. Yeah, industry fabric, absolutely. There we are, textiles. Paisley pattern, that's about dyeing of cloth and textile. And if you want a dye to stick to the cloth, to the textile fiber safely and strongly, then you don't want anything else to be in the way. So the textile industry needed particularly clean water to have very good transfer of the dye onto the fibers. So this was not about human health. This was simply about making textiles prettier. But of course, people realized very soon that there were other benefits. So in the town where I come from, Hamburg in northern Germany, it was Hamburg on the River Elbe, and 10 kilometers downstream, you had another town called Altona, which is now a suburb, but never mind. The people in Altona had one of these slow sand bed filter treatment works for public water supply. The people in Hamburg didn't have it. And when diseases swept through, folk in Hamburg got sick for drinking the normal river water, and folk in Altona were fine because they had these slow sand bed filter treated waters. So very soon people realized that there is much more to it than just industrial uses. It's also about human health, so keeping back bacteria and other substances. So that went for a very long time. And it took another 100 years before rapid filtration was invented. So rapid filtration is very different. It works also with sand, but the water flows through the sand really, really quickly, a lot faster. And that is because you never allow the sand to get dirty enough and old enough for these sort of dirt layers to start growing. So for the rapid filtration, you never have the biological dirt layer through which the water needs to infiltrate. It works only on the physical space between the sand particles. That's why the water flows through much faster. So that's obviously better because as industry and towns and so on developed, there was a much higher and increasing demand for clean water. The problem with all of this is that the rapid filters are nowhere near as good as producing clean water because they work only on particle size. So if you imagine this as a particle, if that was the particle size of the filters. Something of that size will probably be able to flow between the particles. Does that make sense? You know, you have gaps between the particles. So the gaps between the particles are roughly the same size as the particles themselves. That means if you imagine a sand filter, like on a nice beach sand, you look at a grain of sand, and anything that is about the size of the sand grain would possibly flow through a sand filter. So that means that sand filters are absolutely not able to retain bacteria or general solids, certainly not able to retain, say, pesticides or all these other modern pollutants that we have. For that, you would need the biological treatment that you had in the dirty layer on top of the sand filters. But these sand filters have gone out of fashion. And the reason for that is that they are very slow. Like I said, the water flows through slowly, and they're also very time consuming because these dirt layers that sit on top of the sand, they start growing. And the older the filter is, or the longer it's in operation, the more bacteria start growing. And the thicker that layer is, the slower the water filters through because there's just such a resistance to flow. So every now and then you'd have to take the water off the filter, and you would literally have to go in with a shovel and shovel the stuff away, and then you have to start it again. So a lot of effort, very slow, and you need huge areas. So the slow sand bed filters are not really fit for purpose for modern society. That's why people invented these rapid gravity filters, but then realized very quickly that they only remove particles, but not the dissolved toxins. So now we have a mix of chemical pretreatment, maybe even biological pretreatment, and then we use the sand filters only to retain the larger particles. And again, that's more Jachan stuff, but anyway. Just this as an example, you will probably see that better if you download the slides and then look at this yourself. So this is what's called an angstrom size unit. So it's a log scale of particle sizes. And what you have here, roughly around about here, that's the cutoff of a sand filter. So I draw a line there. And that is because here you have the particle size of beach sand. So if your filter is something that is of the size of beach, then pretty much anything that is of the size of a beach sand granule might be retained, but anything that is smaller than that will not get through. So what you get through is maybe yeast cells. Oops, and I didn't want to do that. You certainly get bacteria coming through. You get colors coming through that I mentioned earlier for the pasty. That's where they didn't have sand filters, but the biological filters. And then you get these sort of other things as you go further down. So topical just now, viruses would go through, absolutely no problem. What else do we have that's not so important, not so nice? Synthetic dyes, here, pesticides, herbicides, metal ions, all of that stuff will get through. So really all the things that we concerned ourselves about these days, that stuff here will not be retained by a sand filter. The sand filter will only retain very large stuff, so twigs, leaves, larger cells. And that's why in potable water treatment, again, the stuff that you will go into much more detail with Jachan, what you have is first you have a screen where you just take out dead sheep or whatever floats down the river. Then you have a micro strainer that looks a little bit like the hollow fiber that you might have in your winter jacket. So the water flows along the fiber, and then the clean water goes inside of the fiber and flows along, and the dirt stays outside. And then you do the real trick, and that is the coagulation, which you will do with him, where you add substances to the water that bind all these small particles that would go through the sand filter. So the coagulants bind these particles into larger flocks, and the flocks then are larger than the sand granules, and therefore these flocks get retained in the sand filter. So you can then do some other trickery, so you can use advanced treatment like ozone or ultrafiltration and all sorts of stuff, but that's essentially the design of a water treatment plant for drinking water. You take the very coarse stuff out, you add a coagulant, the coagulant binds all these small particles, and then the flock that is part coagulant, part particles gets retained in a sand filter and chucked away. So that's the end of me ever saying drinking water again. Because for wastewater, it's much different. Like I said already, in wastewater, you have to worry about things like ammonia, nitrogen, phosphate. So these things are nutrients that you want to retain. They are clearly on a molecular basis, so none of this stuff will be retained in a sand filter. You have, generally speaking, BOD, and I have a slide about this afterwards. So BOD is biochemical oxygen demand, which really just expresses how much organic waste there is in the water, how much energy there is in the water that we don't need to release. You worry a little bit about oxygen levels, and that's not so much because the oxygen is bad or good or so for the water. It is because the capacity of the water to retain oxygen is important for when the water is released into the environment. Because fish and the like take the oxygen from the water. So if you reduce the oxygen levels in the receiving environment, then you would starve fish and higher life forms of oxygen, which isn't good. And then you worry also a bit about temperature and the pH of the water and how much solids there's in it. So some of this may not be logical after what I said just now. So why would you maybe worry about whether the water has a pH of 6 or 8? That in itself doesn't matter. But if you're thinking of maybe very particular industries that use, I don't know, maybe particular acids or alkalines to clean metals or have cleaning processes in general, or etching processes and all this sort of stuff, if very acidic or alkaline water was released into the environment, that wouldn't be good for the fish that swim downstream of the wastewater treatment plant. Same goes for temperature. So normal wastewater that comes out of our homes, when it gets to the sewage treatment plant in Scotland anyway, it will be probably plus minus whatever around 12 degrees centigrade all year round. That's because it flows under the ground and we constantly heat it by releasing our showers and washing machines wastewater into it. So it's relatively warm. But when that water hits the natural environment, which may be 15 degrees in summer and 5 degrees in winter, it's not a huge difference, and it doesn't make much difference to the environment into which it gets released. But if you're thinking of a power plant where you have huge quantities of water used for cooling purposes, and you release that back into a river, and if the relation between the water that you use for cooling and what flows in the river is not of the right proportion, then you might actually raise the temperature in the river considerably. And that wouldn't be good because you would create a local change to the environment. So in terms of preserving the environment like it is in that area, it wouldn't be good if you raise the temperature, because all of a sudden the animals in that part of the river would be in subtropical climate. They can't cope with it, and vice versa. Solids. I said just then that wastewater is rich in solids, which is why it's a bit difficult to treat. But once it's going out into the rivers, where you have all sorts of things flowing about in the water anyway, why would you worry about solids? And the reason is that much of our wastewater is collected in a sort of combined sewer overflow system. So a fair amount of solids is washed off the roads into the sewage system. And these solids are relatively heavy, so they're dense, so they settle to the ground quite easily. So if you imagine the wastewater treatment plant discharging lots of solids that stay in suspension, because in the wastewater treatment plant it gets pumped and sloshed and mixed and so on. So you constantly have a mix of suspended solids. If you discharge these solids into a river, and then they would start to settle and they would put a blanket onto the riverbed. And that is where most of the activity in the riverbed happens. It's in the sediment, in the small stones and whatnot that are at the bottom of the river. So if you cover all that in solids, you very effectively kill the river and turn it into a water canal or channel or whatever it is. So it's very important not to have too many solids in there, because they will smother the natural environment that is at the bottom of the river. Right, so these are the wastewater quality criteria, therefore a little bit different than the drinking water criteria, much more focused really on primarily on these sort of things. Yeah, so you have the nitrogen, sorry, the BOD, that's important. You have these fertilizing substances because they would lead to eutrophication if you discharge them into the water. And the other big point is the solids. So those three things are what 95 or more percent of wastewater treatment plants in the world are designed to take out. They're designed to take out organic substances as a whole. They're designed to reduce the load of fertilizers, and they're designed to retain solids. That's pretty much all they, at the end of the day, it's not very much that they do not come back to much later. But anyway. So when you're thinking of the wastewater treatment plant maybe that you're operating or that you want to build, it might be worthwhile looking at sources of that wastewater because different sources of wastewater have different composition. So if you're starting at the bottom, industrial wastewater, you could maybe imagine there's lots of heavy metals in there, maybe chemicals, oil, the sort of stuff you have at the bottom of, I don't know, car workshop or something. So if you're treating that sort of water, you need to concern yourself more with dealing with that. How do you get oil out? So you need an oil and grease separator maybe in the water. If you're thinking of domestic wastewater, that comes out of our homes. That's actually probably of these wastewaters the least damaging one because it has very low BOD. So that means it's not very rich in organic materials. And hopefully that makes sense because what do? We go to the toilet once a day or something, you know, for the big business, and we dilute that big business in about 150, 160 liters of water per day in Scotland on average, because that's the amount of water that an average person in Scotland uses for showering and bathing and doing the dishes and washing machine, cleaning the house and all that sort of stuff. So the concentration of organic material in the wastewater that we discharge is actually quite low. But all the things that I mentioned just then, you know, add a fairly high amount of chemicals to it. So you see these adverts on the TV, people are worried about cleanliness of their hands and wanting to have the babies eat the food from the same carpet that they also have the dogs sitting on, so they throw lots of antiseptics and whatnot on it and make it clean and nice and shiny. All of that wastewater gets generated in a house, therefore is very rich in detergents and antiseptic substances, domestos and all these sort of things. And you're flushing that down the drain, and at some point or the other, it will end up in the environment because what we said just now, wastewater treatment plants are designed to remove BOD, to remove solids, and to remove nutrients. They're not designed to remove detergents or antiseptics or anything else chemical that you throw down the drain. So that's a particular problem actually for domestic wastewater treatment. I come to that later, but really going back to the sand filter is the biological part of it. So modern wastewater treatment plants achieve about 50% of their treatment through the use of bacteria. So you need bacteria in wastewater treatment. And if that wastewater is very rich in these antiseptics, in something that kills 99.9% of all known bacteria, then that obviously is not very good for the quality or for the process that happens in the wastewater treatment plant. So it's a real issue. Going up the list, if you're thinking maybe of paper industry, paper mill has a very high BOD, lots of organic stuff in it to waste paper, but that has a very high carbon content. So with biological treatment, it's always important to have the right balance between carbon and nitrogen in the material, because if you have too much carbon or too much nitrogen, then biological treatment doesn't work very well. So paper mill wastewater is very hard to treat because it has too much carbon, it doesn't digest. And if you go around the countryside or if you have a composting bin in your home, you see that as well. That things like leaves and twigs, banana peel even, they don't degrade very well naturally because they're very high in carbon. Whereas other stuff decomposes much quicker if it has a higher nitrogen content. And then here, food processing, that would be the other extreme, where you have very high BOD but also very high nitrogen content. And that tends to give you a problem with odor because basically you have rotten food. So it starts smelling and getting foul very quickly. Why am I saying all this? Simply because if you get in a situation where you have a problem with your wastewater treatment plant and it might be overloaded with BOD, overloaded with this, that, or the other, it is important to look at where does your water come from and has maybe the mix of influent changed. So if you run a wastewater treatment plant in a small village and all of a sudden you get a large, I don't know, an abattoir or a food processing plant or something starting in that place, then you will have a problem with that. And you then need to change your treatment plants accordingly. Anyway, I keep talking about biological activity a lot, so maybe a little bit more about this. In order to either maintain or reduce biological activity in water, you need to create the right environmental conditions. So you need to have the water at a certain temperature, and the temperature that you generally have in wastewater treatment, the 12 degrees or so on balance in the year that I mentioned in Scotland, is well warm enough for bacteria to thrive. Then you may or may not require oxygen. And that's something we get to later, that you have fundamentally two treatment systems. There's either bacteria that have an oxygen-based metabolism, so they need to breathe oxygen to do their stuff, or you have bacteria that do not need oxygen, and in fact they can't tolerate oxygen, and that is what we commonly refer to as anaerobic digestion. So you use bacteria that do not require oxygen, so to know what you're doing. You might need light if you're talking algae. So if you want to maintain algae in your system, you need to add light. If you do not want to maintain algae in your system, you need to switch the light off. This is why I said I wasn't going to talk about drinking water anymore, but that is why drinking water pipes tend to be made of very dense black plastic. So you get no light into them, so nothing can start growing that needs light. Then different organisms react differently to shear stress. So if you have a lot of agitation in your water, high pressure differences and so on, then some organisms don't like that very much and they don't work very well. So this doesn't obviously apply very much to drinking water, it applies to wastewater only. You need to sometimes worry about that stuff, but it's more of a side issue. And then I mentioned already inhibitors. So if you have too many inhibiting substances in your wastewater, then the treatment systems won't work anymore. So that's why I keep ranting about not putting too much domestos down the drain. So it means that the sewage company has a problem keeping their bacteria alive. And then last but not least, you need nutrients.
Excuse me.
Yeah, fire away.
Sir, please give me an example of the inhibitors in water.
Say that again.
Example of the inhibitor in water, please.
Yes, yeah, of course. So, I mean, the obvious inhibitor, hang on. I don't have one here now. But the obvious inhibitor for starters is things like soap. You know, soaps kill bacteria. So if there's too much soap in the water, then bacteria don't like that very much. Then you have specific substances that are designed to kill bacteria. So antibacterial creams, soaps get also flushed into the water, but it could obviously also be things that are also not good for us. So much of the man-made chemicals that we are discharging into the water all the time will be inhibiting bacteria, whether that is pesticides, for example, that you might not have so much in your house, but you might have them in your garden. You might spray pesticides on your grass to keep the weeds down, and then that water flushes through and ends up in the local river, for example. So, I mean, there's loads and loads of them. I don't want to get into the particular detail of which ones, but essentially the wastewater that we are generating in our homes is full of inhibiting substances because it is full of chemicals that we use in our daily lives. And it's down to simple things as, if you believe the marketing hype, you know, certain deodorants and whatnot have pheromones that attract the other sex and so on. That has then also an effect on wildlife out there. So there's loads of these inhibitors. Nutrients, there's one thing that I didn't mention here. So there's a big gap. What's missing there? I'm drinking my dirty water. What else do you need in water? The right environmental conditions. You need nutrients, micronutrients, same as we need a bit of whatever, calcium, vitamin D and stuff. What else do you need to sustain biological activity? Micro and macro, yeah. Okay. See how this works. You need food, yes. Yes, that as well, calcium. Food. So, a wastewater treatment plant, modern wastewater treatment plant, that is more than just something where you have a filter and get the coarse thing out. It's essentially a biological breeding factory for bacteria, where you create the right environmental conditions. You worry about temperature and oxygen and light and all these sort of things. You make sure that the bacteria are not starved of nutrients, or also you try to reduce the inflow of inhibitors. You have these bacteria and you add food to them, and then they start growing. And that food is the organic stuff that we put down the drain. So the bacteria just basically eat up the waste that we release. Yeah, most nutrients, just looking at the typing there, would be dissolved, actually. Very true. So that's what a wastewater treatment plant in essence is. It is a bacterial farm where the bacteria are held in their trillions to eat all the waste that we discharge down the drain. So we make sure that, well, for the algae, we don't worry about this because we don't really care. But in a wastewater treatment plant, what you need to do is you need to actually supply all the nutrients so that the bacteria do not die and do not stagnate, but that the bacteria, you are on a sharp upward trajectory and they keep growing and growing and growing. And the more they grow, the more they eat the waste that we produce. Problem with that is, once the wastewater is treated in the environment, you don't want all these bacteria, because you do not want to discharge lots of bacteria into the environment, because that's unnatural for the environment. It could change the ecosystem. So the challenge for a wastewater treatment plant operator is that first they have to increase the growth exponentially, and then they have to get all these bacteria out again before they release the water into the environment. Does that make sense? Yeah. So the trick really is to put, you know, a bubble, barrier, whatever you want to call it, around these bacteria that you are farming on your farm. You feed the wastewater through that farm, and then you somehow keep the bacteria out at the end of the farm before the water goes back into the river. And that's what a wastewater treatment plant is. The other thing that I like to particularly harp on about is BOD. I keep talking about BOD and we haven't defined that yet. And that slide is sort of partly wrong because I'm very simplistic. I know this. There's more than animals and plants, and so don't worry so much about the cells. But essentially what you have is you have sort of a divide here in the middle. But some things can just grow on nutrients and lights, and I just keep referring to them as plant, and I know there's other biological distinctions. But other things need substrate, food, and oxygen. So that would be the consumers, yeah? Not producers of food, but consumers of food. And that's exactly what we have in the wastewater treatment plant. You have bacterial cells that take substrate, whether that is sugar or the waste that we discharge down the toilet. We add oxygen to this, and they start using that, and they build up their own cell biomass, and then you know how bacteria work. They get fat, split through the middle. The two of them get fat, split through the middle, and you start growing all these bacteria. So the bacteria are then eaten by bigger things, and you go up the food chain, but it's still the same idea here that you have substrate, oxygen consumption, and you going up the food chain and you build more and more complex organisms that are bigger and rely on the consumption of food. So that's what happens in the wastewater treatment plant, but that also happens out in the wild. So if I add lots of food, nutrients, and substrate into a river, and if there is oxygen in the river, then if there are bacteria in the river, they will do exactly this. They will eat the substrate and consume oxygen. So they take in oxygen and they release carbon dioxide. And that is what essentially we call the BOD. So BOD is the biochemical oxygen demand. That means how much of this here oxygen is consumed when the bacteria in the water digest the waste substances. And that's pretty much a given. If you have a body of water and there are bacteria in that, if you add something digestible to these bacteria, they will digest it. They will consume oxygen. So if they consume all this oxygen, then the levels of oxygen in the water go down, and that is the dangerous thing in terms of environmental protection, because you want to retain the oxygen in the water. If the water became oxygen-free, then it wouldn't be a natural river or lake anymore. It would be turning into an anaerobic digester. All the fish would die first, and then maybe the I don't know, shellfish, crustaceans, all this sort of stuff. And eventually you would be ending up with a foul soup that maybe has a few sort of microworms in it and so on. But other than that, it wouldn't be the river anymore that we want to protect. So the calculation of the amount of oxygen that is being consumed because we put waste into the water, that is what we call the BOD, the biological oxygen demand. So that is a really quite good measure to calculate the amount of waste that's in water, because this substrate, I'm saying here, e.g. sugar, so that could be sugar, it could be, I don't know, iron brew, although that's fat-free, so there's not much in it. It could be bread, it could be meat, it could be all sorts of things. So if we wanted to know really how much waste we release into the water, by looking at the individual constituents of the stuff that we discharge into the water, then you would have to have a really long list of stuff that somebody would have to analyze. If you say so much sugar, and then within the sugar, is it fructose or is it dextrose or whatever it is? So it's pretty much impossible. And in a way, we don't care what is in the water. What we care about is that the oxygen levels in the water don't go down. So all we have to measure is the oxygen consumption. And the way you would do this is you take a bit of water, you add a known amount of bacteria to the water, you add a bit of the test water that you want to find out about to a jar, and you close the lid of the jar, you have a little sensor in there, and you measure how much oxygen is in the water, then you close the lid, and then you come back after 5 days and you measure how much oxygen is in the water then. So the bacteria will have 5 days to use whatever they do. They consume the oxygen, you measure the reduction in oxygen, and that gives you the BOD. In that case, that would be the standard OD. This is turning terrible though. This isn't meant to be BOD, and that's meant to be 5. So you're getting the BOD 5. So 5, the index 5 here means 5 days. And that is the standard measure that you use in industry. You measure the oxygen reduction due to waste in the water after 5 days. And that then is the pretty much universal measure that environmental regulators use to control how dirty the water is. And it's also what operators need to know to identify how much oxygen they need to add to the plant. Because again, that's what a wastewater treatment plant does. It supplies this oxygen demand in the wastewater treatment plant bubble, so that we can then take that water, put it into the environment, and not have experiencing the environment this oxygen demand because the environment isn't able to satisfy that demand. I hope that makes sense. The beauty, therefore, of the BOD5 is that you don't need to know exactly what's in the water. You just need to know what the effect is of that being in the water and what you need in terms of oxygen to compensate for that effect of the waste that is in the water. And all you have to do then is to make sure that the environment is protected because you have a wastewater treatment plant where you supply the right conditions, the right amount of oxygen, and the bacteria take the oxygen demand down so that the environment is protected. Quick recourse to my milk bottle. So I said early on that it's not good to put waste into water if you can at all avoid it. So it's not good to recycle your milk bottle if, in order to do that, you need to pour a liter of milk down the drain. And the reason for that is simply that milk is very, very high in BOD. Obviously, full-fat milk more than maybe semi-skimmed or something. So water has the capacity for oxygen retention that peaks at about 10 milligrams a liter. It depends on pressure and temperature and all sorts of things. But as a ballpark figure, you don't get more than 10 milligrams of oxygen into a liter of water. At about 2 milligrams per, so let me just write this down. 10 is the maximum. And at about 2 milligrams a liter, you start seeing a real effect on sort of natural habitats. So below 2 milligrams a liter, it certainly won't look like a normal river anymore. In fact, some fish and so on start getting wonky at 4 milligrams a liter. So that is the sort of range that you have for healthy rivers, between 2 and 10. So it's only 8 milligrams per liter of oxygen. So that means there isn't much oxygen in the body of water. Obviously, the oxygen will be regenerated because of, I don't know, plant growth in the waters, and because from the atmosphere, oxygen can diffuse back into the water, but that process is relatively small. So or slow, I should say. So if the consumption of oxygen in the water is really high, if the demand is very high, then that demand will outstrip the oxygen flow into the water, and you will really have a low concentration. So that's to be avoided. Then going back to my milk bottle, milk, so standard milk, full fat milk or something, has a BOD of round about 200 K. So a liter of milk has 200,000 milligrams worth of oxygen potential. So a BOD of 200,000. That means, well, we can do the calculations, but that means a liter of milk is 200,000 demand of oxygen versus a liter of water that at best has 10 supply of oxygen. So you divide your 200,000 by 10, and you can calculate that a liter of milk potentially could destroy the oxygen in 20,000 liters of water. So that's 20 cubic meters of water. So you take 20 cubic meters of water, you put a liter of waste milk in it, and that water is not going to be sustaining fish, shrimps, and all this sort of stuff. So that's why I'm saying don't put the milk into the wastewater. If you absolutely want to recover the milk and the plastic bottle, then put the milk into your brown bin with the food waste and the plastic into the plastic recycling bin. If you can't do that, take the milk bottle with the milk and chuck it in the bin. That's better for the environment than washing it out first. Here we go, rant over. Anyway, that's BOD. I hope that makes sense. Have a look at this again afterwards, but that's the main measure that you keep referring to all the time. The other question, and the last question, is by BOD5. And cynical people would say that BOD5 is due to the fact that in Britain there's no place in the river that is more than 5 days of flow away from the sea. So any effect that you have after day 5 doesn't matter, because it won't affect the rivers anymore. Obviously, that would not apply for continental Europe, where water in the Rhine or the Danube or the Elbe or whatever could stay much, much longer than 5 days. That's what I'm saying. It's maybe a cynical view of things. But it is the standard that people say you measure the BOD after 5 days because the bacteria need some time to digest the foodstuff. And obviously the water will flow as well. So that seems to be a reasonable period. Right. And that then, in sum, is what gives you a general layout of a wastewater treatment plant. So it's similar in a sense to the water treatment plant I mentioned first. So you have your raw wastewater going in, goes through screens. So these screens will be just sort of metal bars or something, so maybe the size of my sausage fingers here. So anything that would go through the metal bars would go into the treatment plant, and anything that doesn't go through the metal bars would be raked off and go onto a container, landfill, or whatever it may be. That is primarily to, again, keep out dead sheep and whatever flows down the river, but it's also to a degree to protect the machinery because these smaller particles would get into the bearings of things and so on. Anyway, after that, you get the first treatment. This is preliminary treatment, which is grit separation. So that's the solids that I mentioned earlier on, the solids that get washed down from the road. You put them into a chamber where the water, as it comes through the pipes, is turbulent and mixed and whatever. And you open up the channel, and then the water velocity lowers. So there's not so much turbulence, and therefore there's less energy in the water flow to keep these particles in suspension. And the particles would start to settle at the bottom of your grit separation chamber, where you can then use a rake or a hoover or something and suck them off, and the clean water flows through the grit separation. So now I'm saying clean water. Now you have, after this preliminary stage, you have wastewater that doesn't have sand in it anymore. It still has particles in it, either physical particles that are floating or maybe still suspended. But somebody mentioned earlier on that nutrients could be in suspension. Yes. So nutrients and all these sort of things could also be dissolved. The same as, if that was full fat, there would be a lot of sugar in here. So we have solids in liquid that are dissolved and are still in there. So the overflow here then is really just water that doesn't have the grit anymore. Then you get the first treatment, and that's the primary treatment. That tends to be sedimentation. And it's exactly the same principle as in the grit separation. Apart from that, here you take this a step further and you make the area even larger and you make the tank bigger. So what you have in the primary settlement is water that pretty much looks as if it's in a swimming pool. You won't be able to see a flow if you look at that water. You won't know that anything flows through. It does, of course, but all you're doing here is you bring the velocity of the water towards zero. And that means that particles that are still carried in the water, they will then again settle to the floor, and at the bottom you would have all these particles sitting after a while. Chachan will, or has, I don't know, but he will do the sort of physics behind that. So you can calculate how long it takes for a particle to settle in the water from the top to down here. So you can use that calculation to design the size of the treatment plant, because all you need to make sure is that the water stays in that sedimentation plant long enough for particles to fall from the top to the bottom. That's all there is to it. So after that, you get water overflowing the primary treatment that now has no particles anymore that you could see with the naked eye. But again, there would still be particles that are dissolved, sugar, and there would also be particles that are just so small, like fine dust, that they don't really fall. And again, when you do the calculations with Chachan, some particles would fall so slowly that you might have to wait 100 years. Other particles might have the same density as water. So if there's no density difference, if there's no weight difference, then the particles would never fall out, because if they weigh the same as water, then there's nothing that gravity can pull on. So you still have solids overflowing here. So there's a question there on the chat. In the primary settlement, can we use dissolved air flotation instead of just sedimentation? Yes, you could. Problem is, well, it's not really a problem. You have much more particles that would settle than you have particles that you would get out by DAF. So the primary sedimentation is really the best process that you could use. What you could do is, if you were really concerned, you could have a second stage here, and this doesn't work so well, does it? But you see what I'm trying to write? So you could have a second stage where you have the DAF. It doesn't tend to happen very much. What is more likely is if you really have a problem with sedimentation, then people would also use coagulants. So again, that's another technology that you take out of drinking water treatment. If the sedimentation by gravity alone isn't good enough, then you would add a coagulant to make sure that the particles clump bigger and settle faster. Anyway, after primary settlement, you have primary treated water. You still have dissolved and suspended particles in that. And roughly, as a very coarse, you would have about 50% of the BOD still in the water. So the oxygen demand that the water can still generate after primary sedimentation has only been reduced by about half. So these solids that settle here are only half of the oxygen demand. And maybe that makes sense to you, because if you think of the stuff that we flush down the water, partially digested stuff, lots of sugars, fat, and all this sort of stuff, the highly energetic stuff tends to be quite solvable. So the prime example is sugar. You can generate a very energetically rich energy drink, and you can leave that standing for 10,000 years and you would never have the energy settling out. The only way you can get that energy out is to slow it down and have your body digest the energy, or you evaporate the water and then the sugar would form a crust at the bottom. Do I dare show you this? But like that, yeah, what you have at the bottom of your coffee mug if you leave it standing for long. So this 50% or whatever left of BOD still cannot discharge into the receiving environment, and that's where you have the biological processes. So here you grow your thousands, millions, trillions, billions, whatever the number is, of bacteria. You add oxygen here, which you could do by blowing air through the tank, through sort of diffusers at the bottom of the tank. Or sometimes you also see surface pedals where you just have big sort of almost like water mill pedals that just churn the surface of the water. You can see this quite nicely if you're driving from Glasgow Airport on the motorway towards Glasgow. As you're going over the bridge, if you look to the left, you can actually see these pedals. And you basically just create lots of turbulence, so more surface through which the oxygen can go in. So you're adding the oxygen, and that's exactly the stuff that I mentioned earlier on. In order to sustain these biological processes, you add oxygen, you give the right environment, and you have foodstuff, BOD, adding into it, and then the bacteria start growing and they consume all this BOD and therefore clean the water. The problem that I mentioned before afterwards is you don't want to release all these bacteria into the environment. So what you have after this secondary treatment is secondary settlement, where you have the same process as here, only that in the primary settlement you collect dirt, whereas in the secondary settlement you collect bacterial biomass. So if you're asking me if I'm on a sewage works.
Yes, sir. Sir, actually,
Yeah.
kindly let me know about the exact function of the addition of the oxygen in the biological process.
Say that again?
The function of the addition of oxygen in the biological process.
Yes. What was the question about that?
I'm talking about what is the function of the addition of oxygen in
the function. Oh, I see. Okay. But the function is simply that what you have in here, the bacteria that you put in that biological process are aerobic bacteria. So they need oxygen to digest the food. the same as you and I need to breathe to digest the food that we are taking in. So it's an aerobic process. And like I said before, the capacity of the water, so here you would have water. The capacity of the water to hold oxygen is only 10 milligrams a liter. So that means that you could only treat 10 milligrams of BOD per liter, but you're probably putting something like a ton a day through. So what you need to do is you need to just constantly pump oxygen into the water so that the bacteria can consume the food. Anyway, so question about secondary primary sludges. If I had the choice, if I wanted to fall in a tank, I would fall into this tank, because this tank is full of little bacteria, good bacteria, whereas that tank is full of poop. So that's the difference between primary and secondary sludges. So what happens here is you're basically generating what I mentioned earlier on. You're sort of generating a bubble. That is your biological treatment plant. Yes. So into the biological treatment plant goes the BOD. Into the biological treatment plant goes the oxygen, but out goes nothing but clean water. So you're using up the BOD, and you're using up the oxygen that gets emitted as carbon dioxide, and you're also growing bacteria. And these bacteria you do not want to get into the environment, so you have the secondary settlement where the bacteria settle at the bottom. What overflows is then the treated water. So, 2 lines to this. This sludge you could take off and put to sludge treatment, incinerate it, put it to land, whatever you want, I don't know. But you also take a side stream of this and you feed it back, because what you're trying to do is to keep the concentration of bacteria in this tank really, really high. If you didn't do that, then you would wash out the bacteria faster than they could grow. So you have a bit of return activated sludge, and that's what sewage operators would refer to. They would call this return RAS. So RAS, return activated sludge. So you have a bit of a sludge loop here, but the primary function is to treat the water. Water comes out and is then clean to be discharged into the river. Or it may not be clean enough. If it's not clean enough, then you have to use what we just, as an umbrella, call tertiary treatment. So simply, primary treatment, secondary treatment. If that's not good enough, tertiary treatment. Tertiary treatment could be anything. Tertiary treatment could be the DAF that somebody mentioned earlier on. If you have too much solids, it could be shining UV light added if you have too much bacteria or pathogens. It could be adding a coagulant. It could be all the things that you would probably cover with Chachan anyway for the drinking water treatment side of things. Chemical treatment, ozone, catalysts, all sorts of things. So the tertiary treatment is where we're going beyond the normal plant, because if I try to do this again here, so what I said earlier on, what the sewage works does is it removes BOD, it removes solids, and it removes nutrients. Yes, that's supposed to mean nutrients. BOD, solids, nutrients. So the solids are removed here, primary sedimentation. The BOD is removed here, biological processes. The nutrients we haven't covered yet, we get to that later, but the bacteria also remove nutrients. Next lecture. But what might come out of here might still have, the pesticides in it. It might still have the disinfectants in it. It might still have our pharmaceuticals in it that we take. It might still have, I don't know, any of the stuff that we put into wastewater all the time. So if the wastewater that comes out of here is not clean enough, then we need to use another treatment system to polish it further. We can get to that in the next one of the next lectures. What I'd like to do now is just say tertiary treatment could be another biological treatment. So you could have another biostage here. And you see that sometimes. And the reason for that is that these these bacteria are in contact with the water, probably only for something like 6 hours. So it takes 6 hours for the water to flow through here. So the biological process only has contact for 6 hours. If these 6 hours aren't long enough, then of course you could make this tank bigger. But another option is to have a secondary tank. And there's a logic to this other than size. It's just from a size point of view, it is much cheaper to build one large tank than two small tanks. That's always more cost effective in any process engineering. Bigger thing, it's always cheaper to build than a smaller thing if the smaller things together have the same size or volume as the bigger things. But the reason for having a second treatment, biological treatment system, would be that of selectivity, if you want. So what happens is that the bacteria obviously are competing like anything out there in the wild. So the strongest and the fittest survive. Yeah, the strongest and the fittest grow fast, split, grow, split, grow, split, turn into a big army of bacteria. And those bacteria that don't grow as fast, they get out-competed and they don't really get stabbed at the food stuff here. So the politically incorrect example that I like using for this is to imagine all these bacteria in the biological first stage would be Scottish folk. And the stuff that flows in here would be celery sticks or deep-fried Mars bars. Yeah, that's what Scotland is known for, deep-fried Mars bars. So you can imagine that deep-fried Mars bars are very rich in energy, easy to digest, and they probably make you quite big. So the bacteria would grow really fast. And everybody knows that nobody likes celery sticks, and everybody knows that celery sticks take more energy to chew than they give you, because there's just water and a bit of fiber. If celery sticks were your problem, and if this was the setup where the bacteria only have 6 hours to consume, then you can maybe imagine that if you're feeding Mars bars in here together with celery sticks, you would only get the Mars bars eaten, because the big, heavy, muscular bacteria would eat the Mars bars, the rich, gain, high food first. They would not bother trying to digest celery sticks because they grow much faster on the Mars bars. They like them better as well. So the water that flows out of here, there's no Mars bars in it, but lots of celery. Like I say, if you have a problem with celery and you don't want to discharge celery into the environment, then there's no point having a bigger tank, because they would probably always just sit at the entrance and wait for more Mars bars to fly in. And you would never get folk that really like celery. So the way to deal with this is to have a second treatment plant. Into that second treatment plant, you would primarily have celery sticks flowing into. So in the second treatment plant, you would get a very nice, happy community of vegans that happily eat the celery sticks. And they're not bothered by the Mars bars eating brutes. They just sit here and eat the celery sticks. So you get a specialization of the bacterial population in the second treatment plant. By separating the two communities, the two populations, you get the specialization building up. So you get the coarse treatment here, and then you can build up a community of bacteria in the second separated plant that can specialize to whatever it is that you want to treat. That can include things like these antiseptics that I mentioned earlier on. So most of the antiseptics would just go through here and not be removed. But if you create another environment where there is not very much food, no low-hanging fruit for the bacteria to go for, they still have the drive and urge to grow. If all you give them is stuff that is not very energetically rich, not very nice to eat, but if that's all they get, then they will attack it, and those that are best at attacking it, sort of natural selection, will come to the front. So that's why sometimes tertiary treatment is nothing else than a repeat of the biological process. The big difference is that it's different populations. So you must not mix this sludge with that sludge, because that's the whole point, that here you allow a specialized population to grow. And that was my very first rushed brief introduction from mother sitting with 105-degree arms, or me, on a playground, accepting everything, which is what water is, universal solvent, to the general layout of a wastewater treatment plant. So I thought that's probably 1.5 hours of talking at you. If you want, take the next 20 minutes or so and go over the slides. There's other material online. But I wanted to just get to this point where the main take-home messages, if you want, are that a conventional wastewater treatment plant does this terrible scribbly stuff. It removes BOD in the biological treatment process. It removes solids through the sedimentation. And it removes nutrients. We haven't discussed that yet. That comes next lecture. But BOD, solids, nutrients, that is all that conventional treatment deals with. And conventional treatment is that stuff. Anything that's to the top or right of that line, this here, is conventional treatment. So the water that flows out of a conventional treatment plant will not have made any much, experienced any much improvement in terms of pesticides. You still have heavy metals in there if you want. You have pharmaceutical residues in there. You may even have particularly tricky biological substances that's still in the water. So as we're constantly getting more and more worried about all the other stuff that's in the water and what these micropollutants, we would call them, or contaminants of emerging concerns, also the terminology being used. So anything else than just simply BOD, solids, and nitrogen and phosphorus, anything else that's out in the water, what will be the effect of this? So hormones, for example, people worry a lot about hormones, feminization of fish, changes in populations because if all the frogs and whatnot turn more and more into one sex, then the whole population recreation doesn't work anymore. So how do you get this stuff out of the water? That's where the tertiary treatment comes in, which can be a second step of biological treatment, but it can also be all sorts of other fancy things. And there's the overlap with Chachan's session, because by the time your wastewater has flown through all of this conventional treatment and comes out of the conventional treatment, at this stage, the wastewater is comparable with the quality of the raw water that goes into a drinking water plant, because it's not unlike the water that you would take out of the river to put into a drinking water plant. I would not recommend putting wastewater, treated wastewater, into a drinking water plant. I'm just saying in terms of the quality, it's on a comparable level. So that means that the tertiary treatment includes many, if not all, of the technologies that Chachan will introduce and explain to you as conventional treatment for drinking water treatment. And like I said before, the whole reason for this is that anything that flows here is just far too dirty to be efficiently and cost-effectively treated with these advanced treatment technologies, simply because they would be overwhelmed by stuff that you can just easier get out with leaving it standing for half an hour or turning it into a biological broth for 6 hours. And that's much more energy efficient, it's much more cost efficient, it's much easier to do than this advanced treatment, because the advanced treatment is expensive, energy intensive, and it's much more complicated to run. So why would you waste expensive, energy intensive, complicated technologies for stuff that can be dealt with really quite simply? Anyway, that's what it is. So I'll see you, I think, in 2 weeks' time or 3 weeks' time. If there's any questions, ping me a message or something. And enjoy the rest of your days.